In this DeBacco University video, we're going to see how shielding impacts nuclear charge, as well as how it changes in trends we notice across the periodic table. So when we're looking at nuclear charge, this is the total positive charge of the nucleus determined by the number of protons, represented by the letter Z that we see in this equation. It creates the electrostatic force that attracts negatively charged electrons as described by Coulomb's law. Now, those electron shielding, the phenomena where inner electrons partially block or shield the outer, which are the valence electrons, from the full attractive force of the nucleus. This reduces the effective nuclear charge felt by those outer or valence electrons. The lower nuclear charge means that the valence electrons simply have less pull from the nucleus. They're simply just further away. And we can see that here in these examples of this simplified equation, where Z, which is the number of protons, which would be the atomic number minus the shielding constant, will give you the effective nuclear charge. Again, as that nuclear charge increases attraction, a higher nuclear charge, that increase in electrostatic force is occurring. We see that here. The pulling of those electrons towards that nucleus. We get the negative charges outside and the positive charges inside. Here's a visual representation to see how we're seeing an increase in that. Without shielding, all electrons would experience the full nuclear charge, but inner electrons modify this attraction. So nuclear charge of helium is +2 because of its 2 protons, and as expected, it is more difficult to remove the electron from it than from hydrogen atom, which only has a +1 charge. Seeing an extra strong pulling force, therefore it takes more energy to remove that. That shielding reduces the effective nuclear charge, meaning those inner electrons located at the lower energy levels repel outer electrons because, again, they're both negative, same charge, and partially screen them from the nucleus's center positive charge. This reduces the effective nuclear charge that valence electrons experience and is the shielding constant. It's roughly proportional to the number of inner electrons here. We see this atom here of phosphorus. You can see its multiple rings here. We see just some examples here of the nuclear charge, the inner electrons, and essentially the calculation steps for the effective nuclear charge. Now with that shielding, again, reducing that nuclear charge there, well, here's an example looking at sodium, which, as a reminder, has 11 protons. The core electrons, if we look at the electron basic configuration here, 1s2, 2s2, 2p6, totals 10 electrons. The valence electron is the 3s1. 1 plus 10 will give you the 11. Therefore, the 3s electron feels the +1 charge and not the full positive 11 charge. This weak attraction makes the 3s electron easier to remove and explains why sodium forms a cation or a positive ion so readily. It really only has to lose that one that's way on the outer shell, not really feeling the super strong pull from the nucleus. Therefore, it's really easy to remove that one. It also connects to sodium's low ionization energy and high reactivity, all contributing properties to that removal of that electron. Now, the trend across the periodic table, as we go from left to right, the nuclear charge does increase because simply more protons are being added. The higher nuclear charge is less shielding, it leads to that higher nuclear charge. The shielding stays relatively constant because electrons are added to the same energy level as we're working away or way across that row or period. Now we have that effective nuclear charge increasing steadily. For example, fluorine's valence electrons feel higher effective nuclear charge than lithium, making fluorine's electrons more tightly bound. If we look here again at our periodic table, that fluorine, we have all those electrons being added to that outer shell. We haven't changed the physical distance, get a stronger pull for that. What does that pull do? Well, that will decrease the radius again as we're going from left side to the right side of the periodic table, because those electrons are getting pulled closer to that nucleus. As a result, they're getting pulled closer, it becomes harder to remove them. So that's going to increase the ionization energy. And lastly, the electronegativity will also increase because the atoms attract bonding electrons more strongly as you get closer to those halogens, in this example, fluorine. As we're going down a group or family from top to bottom, nuclear charge is increasing, but shielding also increases even more due to the added inner electron levels. You're getting more and more levels. So what this does is only slightly, maybe sort of kind of increases, but really stays the same for our effective nuclear charge. For example, Cesium's valence electrons are further from the nucleus with more shielding than lithium. Cesium would be right down here. The result as we're going from top to bottom is the atomic radius is increasing because we are adding those energy levels, meaning those electrons are physically further away. It's also easier to remove an electron because you're getting further from that positive charge. And the electronegativity is also decreasing because there's weaker pull on bonding electrons. So the quick summary of all of this is that nuclear charge does drive the attraction of electrons to the nucleus, increasing with more protons. Electron shielding counteracts this attraction by reducing the effective nuclear charge felt by outer electrons, those valence electrons, especially in inner shells, are added down a group. We're getting that physically larger atom impacting that distance and therefore impacting our effective nuclear charge.